So till now what we have seen is basically the basic formulation, the basic optimization function to find a plane W, a plane pi with a normal W that separates our positive points from negative points. And this is what we have seen. Let's understand this function in more detail and also understand what are its problems, right? So first thing first. So what is this? I'll just repeat it, okay? So our objective is to find an optimal W which maximizes. So W star basically means the optimal W or the best W, if I have to put it that way. Optimal basically means the best W. And what does best W mean? Best W means the best hyperplane, because a W or a normal to a hyperplane tells us about the hyperplane, right? We want to find a hyperplane whose normal is W such that it maximizes the sum of these values, right? So remember, this is one pi. This is one plane. There are many such planes. If you think about it, there are many planes that can separate, right? There are many planes. There might be one plane that is like this. There are many planes, and for each plane pi I, there is a corresponding Wi. And our objective is to find the best or the optimal W, which we are calling as W star, which maximizes this, right? So that's what we're trying to do. There are many W's. And what does W mean? As for every plane, there is a unique W, right? If you think about it that way. Now, there are some problems with this. Before we go into the problems with this function, so this is called an optimization problem, right? This is called an optimization problem because we are trying to maximize or minimize something, right? So for this, we'll look at more details about how to solve optimization problems in the next chapter. For now, let's understand this optimization function itself. Right? How to solve it, we'll learn it in the next chapter. For now, what we can say here is, what is W transpose Xi? So let's understand this function alone, right? So what is this function? It is basically argmax of W, summation I equals to 1 to n, yi W transpose Xi. Now, let me call this whole term as signed distance. Let me call this as signed distance, right? Why am I calling it as signed distance? Because W transpose Xi, right, is the distance from Xi to the plane, right? Assuming that W is a unit vector, right? We saw this formulation earlier. In this whole thing, we're assuming that W is a unit vector, right? So this is nothing but the distance. Now, when I'm multiplying with yi, and remember, yi can take +1 or -1 values, right? I'm calling this whole term as signed distance. I'll call this as distance, and I'll call this yi W transpose Xi as signed distance. And what does signed distance do? If signed distance is positive, which means if yi W transpose Xi is positive, it means, what does this imply? This implies that the plane defined by W, pi as defined by W, correctly classifies my Xi. That's what it means, right? Now, similarly, if this is equal to negative, what does this mean? It means the plane defined by W incorrectly classifies my Xi. That's what it means, right? So let me call this as signed distance. Now, all this formulation looks good. We want to maximize the number of points that are correctly classified. We want to minimize the number of points that are misclassified or incorrectly classified. Let's look at an example. A very interesting, of course, this is a cooked up example that I wanted to show you. Imagine if I have my points like this, right? Let me try and draw my points, okay? So let's assume I have my 5 negative points, right? And let's assume I have 5 positive points, right? And let's assume, just for simplicity, let's assume this is my hyperplane. Sorry, let me draw it as a straight line, okay? This is my straight line. This is my plane pi 1. Let me call this plane as pi 1 and its normal as W1, right? Let's assume, just for simplicity, let's assume this distance. Let's assume all these points are at a distance 1. This distance is 1 unit. Similarly, this distance is also 1 unit. I'm just trying to cook up an example to show where this function does not work as well as we expect, right? I'm trying to cook up an example here, right? So I have 5 negative points and 5 positive points, which are, all these points are at a distance of 1 from my hyperplane pi 1, right? Now comes the fun part. Imagine if I have a negative point here. Imagine if I have a negative point here, right? Let's assume this distance now, this distance from the hyperplane is, let's say, this distance, right? This distance from the hyperplane is, let's say, 100 units. This distance is, let's say, 100 units, right? Now let's look at it. Now, if I choose W1, at the end of the day, we have to find the right W or the best W, right? If I choose W1, so case 1, pi1 is my separator, or pi1 is my class separating hyperplane. Then what happens to my function here? What is my function? Summation over. So let's write our function. What is our function? Yi W transpose Xi across all I. Now for each of these points, for each of these positive points, they are on the positive side of the hyperplane because your W1 is on this side. All of them are correctly classified, right? So what are the distance of? So what is Yi? Yi is +1 for all of them. What is W transpose Xi? It is nothing but the distance, right? So for this point, W transpose Xi will be 1. For this point also 1. For this point 1, 1, right? So Yi is also positive. So Yi W transpose Xi for each of these points will be +1, +1, +1, +1, +1, right? What about these points? These points Yi equals to -1. For this point, take this point, right? Yi equals to -1. What about W transpose Xi? Because W1, so let's call it W1 transpose Xi, right? Since my W1 is in the opposite direction, my W1 transpose Xi for this point is -1, right? So when I multiply both of them, I'll get +1, right? Similarly, for this point also, I'll get +1. For this point also, I'll get +1, +1, and +1, right? So in this summation, I'm going to summate over all the points. So first, let's take the positive points. I get 1 + 1 + 1 + 1 + 1, 5 ones. For all negative points, +1, +1, +1, +1, +1. Remember, this is for all the positive points. This is for all the negative points. Now comes the twist. What about this point? This is an outlier point, right? This is an outlier point that is misclassified. So what is its Yi? Its Yi equals to -1 because it's an orange line, right? It's an orange cross, which means it's a negative data point. What is its distance from the hyperplane? What will its W transpose Xi for this point look like? It will look like 100 because it's at the distance of 100, but also in the same direction as W1. So for this point, the final value will be -1 into 100, which is -100, right? So when I summate all of these values, what is the final result here? So +5 + 5 minus 100, which will result in -90. So what are we saying? We are saying that if I choose pi1 as my separating hyperplane, then see, at the end of the day, what are we trying to minimize? We are trying to minimize the sum of sine distances. So what is we are trying to maximize, we're trying to maximize the sum of sine distances, which means at the end of the day, when I apply this function, when I compute the sum of sine distances, I'm getting -90. But look at it, but pi1 seems to be a genuine thing, right? Pi1 seems to be fully logical. Now let me put a twist to this tale. Okay, imagine, because what is our objective? Our objective is to find a best W, correspondingly the best pi, which maximizes the sum of sine distances, right? Which maximizes the sum of sine distances, That's our objective. Let's not forget our objective. Now imagine now if I draw a hyperplane like this. Let me call this hyperplane. Let me just call this hyperplane as pi2, right? And let's assume this is my W2. So when I used pi1 and W1, I got a sum of sine distances of -90. What happens when I use pi2, right? Case 2. Let's write case 2 here. Case 2 is when I'm using pi2 or correspondingly W2, right? So let's assume, just for simplicity, that this distance is 1 unit. This distance is 1 unit, right? This distance is also 1 unit. And distance between each of these points is 1 unit. Let's just simply assume this is 1, this is 1, this is 1, this is 1. Now what happens? Let me draw case 2 for you clearly so that there is less confusion. right? Let's take all my positive values first. I'll just draw it in a different diagram. 3, 4, 5, right? And I have all of my negative points here. 1, 2, 3, 4, 5, right? And what is my separating hyperplane look like? My separating hyperplane looks like this, right? This is my case 2. I've written my case 1. In case 1, let's not forget this. I got a sum of sine distances of minus 90. So in case 2, let me write this as case 2. In case 2, I'm using pi 2 or I'm using W2. So this is my pi 2 with a normal of W2. And where is my other point? Where is my crazy point or outlier point? My outlier point was here. Now, since this is W2, what will happen? It will declare. So my pi 2 will say all of these points are positive because it's on this side, right? So my pi 2 will say that all of these points are positive and this point is negative. Right? Let's assume just for simplicity that the distance between these 2 points is 1 unit. Distance between these 2 is 1 unit. Distance between these 2 is 1. Distance between these 2 is 1 and similarly 1. So similarly, let's assume these distances are 1 unit. I'm just trying to construct an example to show you that the problem that we have, that we are solving, which is the sum of sine distances, can be incorrect. Okay, I wanted to construct an example for you. Let's assume this distance is also 1. Okay, now let's do summation of yi w transpose xi, w2 transpose xi, right? For I equals to 1 to n. So what does it look like now? Let's look at it. This is the important part. For this point, this is a positive point, right? This is a positive point. And it's at a distance of 1 unit, right? So yi equals to 1, w transpose xi equals to 1. So this will be plus 1. The sum of sine distance, the sine distance for this is plus 1. The sine distance for this similarly is plus 2 because it is at a distance of 2 and it's a positive point which is on the positive side. Remember, this is the positive side of the hyperplane and this is the negative side of the hyperplane. Let's not forget those basics, okay? So for this, the sine distance is plus 3. For this, the sine distance is plus 4. Sine distance is plus 5. What about these? This is a negative point that is on the positive side, but at a distance of minus 1, which means its sum of sine distance will be minus 1. Similarly, sum of sine distance is minus 2, minus 3, minus 4, and minus 5. What about this point? This point is a negative point, right, on the negative side. So its sum of sine distances will be plus 1 because it's a distance of 1. Now let's sum up all of them. We'll get 1 plus 2 plus 3 plus 4 plus 5, right? Okay, with minus 1, minus 2, minus 3, minus 4, minus 5, and plus 1, right? This is for all the positive points. These are all these negative points, all these 5 negative points here, and this is for the outlier point. Now, when I sum up all of the sum of sine distances, what do I get? So these will cancel out, right? I'm left with plus 1. Now remember, now the fundamental question is when I do sum of sine distances with W2, with this hyperplane, I'm getting a value of plus 1. When I do sum of sine distances, with pi 1, with this hyperplane, I got a value of minus 90. And what is our objective? Our objective is to find, let's never forget our objective. Our objective was to find a W that maximizes sum of sine distances. Let's not forget that basic stuff. Now, imagine if I have to choose between these two pi's or these two pi 1 and pi 2. So let's assume this is my pi 1, this is my pi 1, right? And this is my pi 2. Which one will I choose? The sum of sine distance for pi 1 is minus 90 and the sum of sine distance for pi 2 is plus 1. Since plus 1 is greater than minus 2, I will choose pi 2 as my classifier. Plane 2 as my classifier. But if you think about it intuitively, so this is what the optimization problem is resulting in. Remember, if I try to maximize sum of sine distances, in this specific example that I built, it's a simple example I'm building. It says that pi 2 is a better classifier. But if you think intuitively, right, pi 2 is a terrible classifier because let's look at it. What's happening in pi 1? In pi 1, 5 positive points are being correctly classified. 5 negative points are being correctly classified. Only 1 negative point is being misclassified. So 5 positive points correctly classified, 5 negative points correctly classified, 1 negative point misclassified, right? In the case of pi 1. In the case of pi 2, what's happening? 5 positive points correctly classified, 5 negative points misclassified, and 1 negative point correctly classified. So here, if you look at accuracy, right, it's 5 out of, so there are 5 mistakes. There are 5 mistakes out of 11 points, which means its accuracy is 6 by 11 because there are 6 correct points here when I choose pi 2. What about when I choose this? When I choose this, I have 10 by 11 points which are correctly classified. So intuitively, if you think about it from a commonsensical perspective, pi 1 is better than pi 2, right? So intuitively, or commonsensically, if you think pi 1 is better than pi 2, But what is happening? Because I'm using this maximizing of sum of signed distances, because I'm using this, it's saying pi 2 is a better classifier, which is incorrect, right? And why is that happening? It's happening because we have this extreme point. Because it's happening because we have this extreme or outlier point, which is very far away, which is favoring, remember my terms very carefully, because of a single outlier point here. In this simple example that I built, this single outlier point or extreme point is preferring pi 2. It's now, if you think about it, if this was my optimal pi, because of this one outlier, right, my whole hyperplane, the best hyperplane became this, which is incorrect, isn't it? So one outlier is impacting, one single outlier is impacting my whole model, which is a terrible thing, right? Remember, one single extreme or outlier point, one single extreme or outlier point is impacting, is changing my model. Why am I saying model? Because a model is nothing but a hyperplane in logistic regression. My model is nothing but a hyperplane. And this is very bad situation. This is very bad. We should never be in this situation because there are always outliers, there are always extreme points, erroneous points in data. If a single point or if one point is impacting my model this badly, then something needs to be done. So maximizing sum of signed distances, can be impacted. It is not outlier prone. Which means outliers can impact it a lot. So now we need to somehow change this. We somehow need to modify this formulation. So what was our formulation here again? Our formulation was this mathematical function. So we need to modify this. We need to modify this now such that outliers do not impact it much. And how do we do it? We do it using a technique called squashing. And the idea of squashing is this. Now let's go back to our example. Now if you take pi 1, in pi 1, this was the problem, right? Why did it become minus 90? Everything was good except for this point. If you look at the distances, if you look at the sign distances that we added up, all these were great, right? All these were also great. The problem arose just because of this distance being very large. So what we can do as a hack is this. So right now, what if, the idea is this, the big idea is this. So instead of using sign distance, instead of using the simple signed distance, right? Instead of using signed distance, what if I make this modification, which is if the signed distance is small, okay, use it as is. Don't change it much. But if it is large, if the signed distance is large, make it a smaller value. So imagine in this example itself, I'll try to explain you with this example itself. Imagine, see the distances from pi 1 for each of these points, the distances for pi 1 for each of these points is small, right? From pi 1. So if the distance is small, don't change it much. But if the distance is 100, don't use 100, do some lesser value of 100. Okay, so how do we do it? Now let's look at it through simple geometry and functions, right? The way to do it is this. Imagine, this is the interesting idea, right? Imagine if this was my signed distance. Imagine if this was my signed distance. What is signed distance? Yi W transpose Xi, right? Signed distance with respect to a plane W, right? So as signed distance increases, let's assume this signed distance is 0. Okay, so what do we want? Okay, what do we want? As signed distance increases, right, as it is positive, as it increases, we want it. So for example, at 0, let's assume it has some value. The signed distance at 0, let's assume it has some value. It could be 0 itself. We'll see. Now, as we go farther and farther away from 0, right, we want this to increase. Because these values are small. Let's assume up to a value of 10 or something. Let's just say this is increasing linearly. Now, this is what I will use. Let me call this as a function of signed distance. Okay, let me call this f of signed distance. I want to come up with a function of signed distance such that when signed distance is a small positive number, it will grow smoothly. But once it becomes large, let's assume once it becomes 100, this smooth function will taper off. This is called tapering off. This is called tapering off of a function. What does it mean? Which means as my function increases, when it is small, when my signed distance is small, this is also increasing normally. But when it becomes large, it will not increase. So if I increase linearly, it should be this way. But what I'm saying here is don't increase it linearly. Once it becomes large, just taper it off such that the maximum value will never be more than something. Right? Similarly, when a point is, see, when is my signed distance negative? So up to minus 10, reduce it normally. Right? Reduce it normally. But beyond that, taper it off. Such that, so now when you taper it off, what happens? Let's look at again geometrically, right? When you taper it off, what happens is, okay, probably it's better to draw a completely new diagram so that we don't get confused. Assume that this is my hyperplane. Okay, let me draw it properly. Let's assume this is my hyperplane W. Sorry, pi with a normal W. Now, if a point is close, I will just use its distance. Let's assume this distance is 1. Similarly, if a point is at a distance 2, I'll use this distance 2. Let's assume this is correctly classified point. Right? Let's assume this is a correctly classified points. But when a point is very far away, even though its distance, let's assume its distance here is, let's say 100. I will not use 100. I will use some value which is much less than 100. Right? That's what this function says, right? As the distance increases, I will not use exactly the same value. I will ensure that this value is no more than, let's say I'll ensure that this value is, I'll not use 100. Let's say I'll just use no value more than 5. Even though, so for any value which is 5 or more, I will say I will not use a larger value because of this single outlier, my whole model can change, as we saw earlier. Right? Here, just because of the single outlier, my whole model changed. And that is because of signed distance creating this problem. What if instead of my function, so what am I doing here? So what was my original function? Ya W transpose Xi, I equals to 1 to n. Whenever I don't write I equals to 1 to n, you can easily assume that it's I equals to 1 to n, right? This was what we were solving earlier. So with this, there is this outlier problem. So what are we saying? Let's not solve this. Let's solve argmax of W summation over I equals to 1 to n, some function of Wi Ya W transpose Xi such that this function behaves like this, where as the distance increases, so what is this? This is signed distance, right? This is nothing but signed distance. Now how should this function behave? This function should increase normally, but beyond a point, it should taper off. And we want such a function. And one such function. So we are converting this problem to this problem so as to get rid of the outlier headache that we have. And one such function f is called the sigmoid function. One such function is called the sigmoid function, which is often written as sigma of x. So let me explain you what is sigma of x first, right? So sigma of x, so now our f of x is nothing but sigma of x, right? So what is sigma of x? Sigma of x is written as 1 by 1 plus e power minus x. Okay, this is what, so how does this look? So let's understand how this function looks, right? So if you have x here, if this is your x, 1 by 1 plus e power minus x looks like this, right? Sorry. Okay, why don't we just use Google for this? Actually, I really like to plot things with Google. Okay, so let's do this. Plot, right? 1 by 1 plus e power x. You can actually, Google has some very nice plotting tools. 1 by minus x. Sorry, did I write plus x or minus x in the diagram there? Minus x, right? So it is 1 by 1 plus e power minus x, right? So if you look at this function, Google has this very nice tool, right? Instead of you plotting all the time, you can just say plot 1 by 1 plus e power minus x. This is what is called sigma of x, right? Sigma of x is 1 by 1 plus e power minus x. E is basically the exponent function. Now, instead of me drawing it like crazy, let's actually look at Google's drawing, okay? How does this function work? Let's look at it. So if this is my x, when x is small, let's assume when x is small, this is almost linear. This is behaving like a linear function, right? If you see this is almost like a linear function. But once x increases a lot, it will taper off as we want. Similarly, when x is small negative value, right? It is almost linear. It is almost linear here, but it immediately tapers off. And what is the maximum value here? The maximum value is 1 and the minimum value here is 0 because this is 0.2 and this is 0. So sigma of x has a maximum value of 1 and a minimum value of 0. Right? This is good. And sigma. So what is our x now? Our x is nothing but our sign distance. Right? Because what are we doing it? Let's go back to the formulation. We are saying we'll change our formula. We'll change our optimization problem as argmax of w summation I equals to 1 to n sigma of yi w transpose xi. Right? So this is what we want to change our problem to. And if we change our problem, what happens? As the distance from the hyperplane increases, when it is small, this will increase almost linearly. This is almost like linear growth, right? Almost. It's like a straight line. By linear, I mean it's like a straight line. But beyond that, it will taper off. Its maximum value is 1, minimum value is 0. Now here is the fun part. What happens when the distance is 0? When the distance is 0, this value is 0.5. Okay, so let's write down. So sigma of 0 equals to 0.5. These are the properties of our function. This is called the sigmoid function. For the sigmoid function, the maximum value is 1, the minimum value is 0, sigma of 0 is 0.5, and when the value is small, it is almost growing linearly, but beyond that, it will taper off. So we have this tapering that we actually looked for. So that when a point is very far away, we are not going to give a value of more than 1. Right? Now, the reason there are many functions like this. There are many functions that have this nice behavior of a linear growth here and then tapering off. There are many functions in the universe that can do that. But the reason we choose sigma, there are multiple reasons. One such reason is it has a nice probabilistic interpretation. It has a nice probabilistic interpretation. Let me take you through the probabilistic interpretation. Right? It has a very nice interpretation. The interpretation is as follows. Okay, let me show this to you. When a point, imagine this is my hyperplane, right? If a point is on the hyperplane, let's assume I have a point on the hyperplane, right? So by probabilistic interpretation, what this returns to me is, it returns to me the probability of a point, probability of yi equals to 1 is what it will give me. Suppose, imagine, take this simple example, right? If you have a point, if you have a plane like this with w, if a point is exactly on the hyperplane, then its distance equals to 0. If a point is on the hyperplane, then its yi w transpose xi equals to 0 because its distance equals to 0, right? When a point's distance from the hyperplane equals to 0, what is its probability that its yi equals to 1? Right, sorry, if w transpose xi, sorry, not yi. If w transpose xi equals to 0, which means its distance equals to 0, what is the probability that it's equal to 1? It's roughly half because it can either be positive point or negative point, isn't it? That's the fun part here. So if a point lies on the hyperplane, which means its distance equals to 0, right? Which is exactly this. What is the value? 0.5. We just saw this, right? Sigma of 0 equals to 0.5, right? If a point is very far away from the hyperplane, suppose, imagine if this is my hyperplane, if a point is here, if my query point is here, then what happens? My W transpose Xi is very large and it's positive. It's large and positive because it's on the same direction as this. So when a point is very far away from my hyperplane, right, my W transpose xi is very large. When my W transpose xi is very large, right, my what is the value when this when this W transpose xi becomes 12, right? What happens? My probability value becomes 0.999999. You see this 0.99999. So if a point is in the same direction as my W, and if it's very far away, then its probability that yi equals to 1 is very close to 1. Right? So there is a nice probabilistic interpretation to sigma to the sigmoid function. Now what we can do is, instead of optimizing the original problem, which was here, right? Instead of optimizing, so let me write it. Actually, it's better to write it in English. What were you originally maximizing? Maximize sum of sign distances. This was what we were optimizing, but this has the problem with outliers, right? So what did we do? We found a function called sigma, okay, which is the sigmoid function, which has all the nice properties that we want. What are the properties we wanted in this function? We wanted a tapering behavior. We wanted a linear behavior when the value is small, tapering behavior when x is large, and it has a nice probabilistic interpretation. So what did we do? Now we are going to maximize sum of, okay, let me write it this way. Maximize sum of transformed signed distances. And what is this transformation? This transformation is using the sigma function, because sigma function has this nice interpretation, right? Now what does my problem look like? My problem looks like this: argmax of, so W star equals to argmax of W, summation of I equals to 1 to n, sigma of yi W transpose xi, which if I want to write it in full form, it's argmax of W, summation of I equals to 1 to n, 1 by 1 plus exp. Exp basically means e power minus yi W transpose xi. Remember, because sigma of x is 1 by 1 plus e power minus x. The minus symbol comes from there, right? It's not an error. The minus symbol comes from there. This minus symbol is here, right? This is the problem that we are going to solve now, right? And this is less impacted. This is less impacted by outliers than your simple sum of sign distances. That is our whole idea here. That's the idea of sigmoid functions, and also the whole problem of getting rid of outliers and squashing. This function is also called squashing, remember. So it's called squashing because of the very nice idea. Because given distances, see, your distances from the hyperplane can range from minus infinity to plus infinity. And given some values in minus infinity to plus infinity, it is squashing these values. So this is called squashing. It's also called squashing, because squashing basically means it's converting distances from minus infinity to plus infinity, right? These are my distances, right? My sigma function is squashing those values between 0 to 1. My sigma function is now squashing values between minus infinity to plus infinity between 0 to 1, such that when the values of x are small, it is almost linear, but it has this tapering off behavior. Now you might ask, why are we using the sigma function? There are hundreds of other functions that can do it. Those of you who are more well versed in mathematics, sigma function, remember, it's very easy to differentiate. I'll come back to these points little later. It's very easy to differentiate, and this has a very, very nice probabilistic interpretation to things. It has a very nice probabilistic interpretation to things. There are many functions. Now you might say, why should the ease of differentiation be important? You'll learn that in next chapter, because to find maximum value or minimum value, to actually solve this optimization problem, you need a function to be differentiable. Those of you who have forgotten basics of differentiation and calculus, don't worry, we will revisit all of them. Machine learning requires functions which are differentiable. You'll understand why in the next chapter when we delve deeper into, when we understand calculus, when we understand why calculus is important to the real world in the next chapter. Remember, those of you who studied calculus in 11th and 12th class, or your PUC or pre-university or K11 or K12, you'll easily understand this. This is simple. This is not some advanced calculus. This is simple calculus. I promise you, it's very, very simple for you to understand. right? So the probabilistic interpretation is also important, because remember, what are we deriving? So we are deriving right now, we are deriving logistic regression, right, using geometry. Right now, till now, since the time we started this chapter, we are trying to derive logistic regression using geometry. You can derive logistic regression in two other ways. You can derive it using probabilistic method, using probability. The way we did naive Bayes, remember? We'll cover this in brief, and I also give you some pointers where if you want to study the probabilistic interpretation, if you want to study the probabilistic interpretation of logistic regression, you can study it in deeper. But we are using geometry right now. We are deriving the whole of logistic regression using geometry. There is a third approach called loss function based derivation of logistic regression. We'll also cover this in detail, because this is very useful for us in understanding other techniques. Okay, so we will cover this in detail, which we are doing right now. We will cover this in brief, right? And I'll give you some pointers. I'll give you some pointers for those of you who want to understand deriving logistic regression from basic principles of probability. You can do that. Okay, this loss function will go and deal with it in detail, by the way. Okay, so right now we are taking this step. We are trying to derive logistic regression through geometry, because it's easy. I could have derived it using probability also, but it will be a lot of mathematical modifications, and people often lose the geometric intuition when you go too deep into probability. It's not easy to connect probability with geometry. Geometry is much more easy. At least the way I see it is, geometry is visual, and hence we can understand things much more easily using geometry. But I promise you, we'll see all these three interpretations of logistic regression, or three derivations of logistic regression, by the end of this chapter.